the sandwiches.
There will be sandwiches downstairs.
Okay.
Yeah.
Downstairs. And so we can continue to visit the posters and keep the conversation going during lunch. Without further ado, let me introduce the next speaker, who is Professor Cristiano Oliveira from the Physics Institute of the University of São Paulo, who's going to talk about structural investigations of soft matter systems.
Thank you, Andre, for the kind invitation. It's a pleasure to be here. I'd like to thank the organizers for the kind invitation. So, as said, I'll talk about some experimental methods to investigate structure. As you see, it will be a different line now, not so much a few equations, but some applied stuff, let's say. So we are interested on measure things. So then we have to think about length scales. And when we think about length scales, we can vary either from atoms or atomic structures up to large systems. And in order to investigate this type of system, you have to have experimental methods. Depending on the length scale, you can use different types of methods, either from, let's say, microscopy methods, where you can really see things in real space, or almost this in 2D. But usually, when you wanted to have structural information, you can use X-ray or neutron scattering and diffraction. And this will be some of my focus here. I will talk about small angle scattering, which, as you see, can give some information about the overall shape and overall arrangement of the system. This will be clear now with the examples. This is the typical setup. You have a source where you generate your photons. For example, you collimate your beam, you strike your sample. If we are talking about X-rays, this will interact with the electron clouds. You have scattering, and from the analysis of the 2D image that you generate, you can have some structural information. This is a very, let's say, flexible method. You can study solutions, solids, gels, etc. We used to say that we are that we have low resolution, meaning that we will not see atoms, but we will see agglomerates, and we may have a very nice ensemble average because we are illuminating millions and millions of particles. And also you can investigate amorphous systems, which is very useful when you deal with soft matter. So I won't get into all the details, but usually you can have either fixed particles or randomly oriented particles. We are interested, let's say, in the particle shape, but we measure the intensity. So as you can see, it's not simple to invert this formula. So then we can apply several tricks or several methods to do the analysis. When we have fixed particles and we do scattering, we can have anisotropic images, as you see several examples. And when we have randomly oriented particles, you can have this azimuthal symmetry, which in some cases can make the analysis simpler. So you have to collect data. We have now series, which is the new synchrotron in Brazil, which is actually available now. We have several standard SAX beam lines, also some coherent SAX beam lines. But in order to really go through a synchrotron and have the best as you can, it's necessary to do some prior analysis. And for this, we have a very nice SAX infrastructure there in the Institute of Physics. it's a multi-user center that we have 3 machines. You can enter in the site for more information, but basically these are the snapshots of the instruments. One of these machines, Zeus 2.0, has 3 sources: copper, chromium, and molybdenum, with the different energies which are useful to investigate energy dependency when it's necessary. It's a big instrument, 10 meters, so you can go either from very small angle up to wide angles. And I will show some results from these instruments right now in applications for investigation of particle interactions, nanoparticles, liquid crystals, and hair. So, particle interactions. We saw here several models for lattice analysis, etc. And but when you measure things with X-rays or even neutrons, you have a very good indication about particles interactions and correlations. So this will be some of the topics here. And for this, we are investigating the evaporation of water in particles using sacs with in combination with acoustic levitation. This method of acoustic levitation is very interesting. It was mainly used in synchrotons because of the high flux. Basically, the idea, as I mentioned now, is you measure everything in air. You generate some acoustic waves, and then from the setup you can have particle trapped in this point or in several points, and then you can investigate this in real time using scattering. Here we'll have one example. This is another one where they were investigating the multilamellar systems, and this is for protein aggregation, but there's not yet in the literature applications of this in laboratory equipment, and this is one of our ideas. So basically, the overall idea is to generate a stationary wave, and then from when you have pressure nodes, you can grab not so heavy particle, very light particles. So I want to get into all the details, but my colleague Marco Brizotti is specialist on it. And then we build up some setup that I will show now. So the idea is to investigate the stability or concentration effects of colloidal systems. The stability in this system is very dependent on the concentration. And then if you investigate the effect when you vary the concentration, you can have information of phase transitions, etc. But since we are dealing with liquid samples, usually you have to have a vessel to hold your sample. But as you see, we using acoustic levitation, we can measure without vessel. But our idea here is, in order to increase the concentration, you can increase the quantity of the particle of interest, putting more and more solute, or to remove the solvent, keeping the number of particles fixed. This is not tricky or simple to do, but this is what we will actually do. And for this, we use acoustic levitation. My colleague has several articles on this. And together we build up a setup, as you can see here, and you can actually grab water particles. So as you can see here, we have a very small water drop here, and we can mount this inside of the chamber, and you can press X-rays on it in order to increase the scattering power. We use liquid crystals. This black spot here, which is actually in 30 seconds, already give to you very strong scatterings. And since this ferrofluid is water based, they evaporate. And simply, if you leave it there, they will evaporate, and then the ferrofluids inside will increase the concentration, and with this, you will have more and more structural factor effects, and you can model this. Apply some modeling method, and you can follow several parameters. So this is a current work that we are using for different types of systems. Nanoparticles. One key point is to investigate the synthesis, principally when you are doing bottom-up synthesis procedures, and in order to investigate the growth, we can use scattering methods. This is a collaboration, a long-standing collaboration that I have with colleagues from German, Professor Matthias Epple group. And basically, one of the goals is to investigate how the nanoparticle synthesis happen. And for this, we use in situ investigations. This is basically, you have your synthesis vessel. You take some small part of it, pass through the sample using a very static pump. Using this sample holder, it went back, and you can follow this over time. This is an actual view of this setup, and you can follow the synthesis over time. These are 1 minute frame, and you can see, well, we have some curves. We can model this. This is basically what we showed in this already 4 years old article, and we can, as you can see, we can model the whole evolution. Has some sizes information, and in this case here, we could more or less show that, well, initially we could see some signature of coalescence behavior for the particle growth, and then later in the late stage, we could see what is called overall post-round ripening, which is some models for the particle growth. Recently, we also applied this for the smaller particles, for ultra small nanoparticles, which are trickier because since they are very small, they scatter less, but still we could follow. This is time in seconds, okay? And we could follow some trends. This is a work in probe sponges to show to you that things can evolve. Liquid crystals. My group, which is led by Professor Antonio Figueiredo Neto, has a long tradition in liquid crystals investigation, and in 2022 we come out with this article here, which showed us, where we showed for the first time a method to model the structural factor and the form factor of the arrangement of the liquid crystals. As you know, liquid crystals are basically anisotropic molecules that can arrange themselves in different ways. You can form the so-called matrix structures, matrix, chiral, etc. For until a few years ago, it was one of the key applications for this displays. Now with the LED revolution, this is not so much in use anymore, but still you have several other effects because you have very interesting light polarization effects. Since these models or their size fields or are within the nano scale, when you use X-rays, you can have very interesting data. This was actually seen for the late 70s or early 80s, where my colleagues and also via Amaral showed that, well, SACs can give you some very useful 2D images or 2D data. But the analysis of these were, let's say, qualitative, and then we work out some methods for this. First, we reproduce this data there in our system, as you can see here, and then we work out some methods first, some methods to estimate the parameter, which we can do for doing this azimuthal or radial integration, and then you can work out some methods. Here I work out a model where you can introduce the fact that you can have aggregates, you can have pseudo-laminar system, particles are elongated, so you group it in a single model. You can fit cuts because now you have anisotropic images. So you can do cuts on it, and then by fitting the cuts, you can have different or very interesting structural information. It's a long story. First thing we show that the particles or the liquid crystal particles can be seen as core shell particles, and then using this, we can model the full system where we fit either the parcel size and also their overall arrangement. More details can be seen in this article, and then after having this, a colleague from Swiss came to us and said, "Well, I have a few images from synchrotron." She was lying; it was hundreds of 2D images, but then she asked, "Well, we have microscopy data, radiology, but we cannot deal with the SACS data." But then we joined forces and we managed to understand how the process, and this was in this article here. I just go by because of the time. We also are investigating hair. I entered in this field a few years ago. I had no idea how interesting it is. For sure that it's a hot topic because everybody has hair. Some people more, others less, but still we have it. Some people interact, etc. And in this work here, which was cover of the Journal of Applied Crystallography, we investigate structural interactions or structural effects of two very famous or very useful ways of changing hair, either hair straightening and hair bleaching, and we applied a bunch of methods for investigating this. The overall idea is to understand what happens to hair when you do chemical and heat damage. We have several ideas or several expectations of what can happen. So basically, we use the so-called certified hair. You cannot simply take your hair and you have to buy certified hair in order to really show that people can reproduce this. And then we use some saloon procedures for doing bleaching and straightening. We have my colleague Sibeli Lima. She knows everything about it. So we learn a lot from her, and then we did this for the several samples that we did. As you can see here, we have samples for bleached, straightening, and also bleached and straightened hair. I want to get into about the details, but when you use optical microscopy, you can actually see that virgin hair, you have a very nice external part, but then when you do bleaching, etc., you changing the structure. This can be even worse when you do some images. You can actually see what happened when you hit a lot your hair. You can explode, etc. You can see what happened in the thermodynamic signature by treating hair. We can see that the treatment changes some of the enthalpy values, which means that the hair becomes weaker. And we have several SACS data, but here I just showed that we can follow in situ the hair heating. And then, as you can see, things are changing here, meaning that hair is losing its structure, and we can group all this together as we did in the article. So I know it was fast, but I hope I could show to you that using scattering methods, you can investigate soft matter system. Even you have lower flux in a lab system, a good point is that it is always there. So whenever you have a sample, you go there, measure. So it is very useful for fast screening and also emergency measurements. This happens all the time. This is, we can, the machine that we have there, we can very easily the distance. So we can go to ultrasound, which is allow us to see large particles or large correlations or sizes, to wax, which is almost atomic structures. And this is a very, we have more and more users in Brazil now having their own SACS instrument, which is good for the community and also for the new secret. So thank you for all the collaborators, the agencies that allow us to have fun with science, and you for your attention. Thank you very much.
So we really have a question here.
Yeah, in the last slide, when we were talking about liquid crystals, you showed, for instance, some collaboration with someone from Switzerland.
Yeah.
I noticed that you had both rheological measurements and structure measurements. Can you combine the two methods?
Yes. This is a very nice question because
Structural and rheological.
Yeah. Nowadays in the synchrotrons or even in the lab, you have this simultaneous measurement. This was not done simultaneously, but actually we just applied to FAPESP to have a real SACS instrument in our lab, so we will be able to do both in real time. Yes. Okay.
I have a question.
Yes.
About that slide you showed the what's more happening. You found, I think, the exponent half to the process of the merging droplets.
Okay, yeah.
I have a question about this because in the what's more happening we have in the classical,
This one, yeah.
the classical exponent is 0.33. What happened in the second case because it increased the exponent?
Actually,
That scale?
it's just right. First, we have this coalescence, which is a model where you assume that particles would merge and form larger particle. And in this case here, small particles diffuse and the atoms go to larger particles. This is usually models, and then these are signatures that you can follow in your data. Okay,
Thanks.
you're welcome.
I think this explains why you are seeing different exponents in your case.
Maybe.
Because you have a little bit of both.
Yeah.
Exactly.
More questions?
Professor, thanks for the talk. About the acoustic limitation, is it too difficult to adapt the setup to any exact setup, or is it simple?
I mean, as long as you can put there and pass your beam, it's okay. But the point is you have to have space in your chamber. Okay, so we have several setups now, and right now we have this. A problem to use this in a synchrotron or series that since you have a lot of photons, this will simply burn your sample. So, but this can be also be done there for sure. Okay.
The vacuum of their sample.
No, this has to be done in air.
Oh, yeah.
But for sure that what we do, we have nodes, etc., in order to keep the air space lower as possible. Okay. Oh yes.
Yeah, thank you, Cristiano, for the
Thank
nice
you.
talk. So I was just curious, I mean, what's the advantage of doing this acoustic limitation experiment? What do you gain in terms of information?
Well,
This is very cool, I mean.
in this thing, so as I mentioned, to the investigation of concentration effects are free here. They simply happen, and this allows you to do several things for the lack of time. I just showed this, but we did this for multilamellar vesicles, proteins, etc. So you can use this to as a tool.
Way of getting it solved out.
Yes, or in other words, to investigate in an easy way the effects of the increasing of the concentration, which is not simple. Okay.
You may have said this and I missed it, but do you have to worry at all about internal vibrational modes of the droplet itself, and how do you handle those?
I mean, you are measuring everything there, right? And from the simulations we did, we know that these particles rotate. So in my students' project, we are combining this with Helmholtz coils in order to see if applying a high magnetic fields we can trap things there. But it's a work in progress. Okay. Thank you very much.
So, any more questions? In the fact that the whole object is vibrating, rotating, is it a blessing or a problem? Because if it is rotating, you can sample it better, maybe, or
Right now, we simply use as it is, but we have a different version now where we can move drops, and then you can have a fixed drop, and then you can move another on it, so you can follow in situ reaction, etc. For sure that you have some problems because when you join drops, they vibrate, changes shape. But if you keep your beam small enough, you can still investigate without so much problem. Okay.
But so I was wondering about the same thing that she asked, and I think that probably the time scale related to the full rotation of the molecule is not so important. But what about what about the microscopic vibrations?
I mean, again, here we are talking about a drop with 2 millimeters in size. We have a beam with 0.3 or 0.4 millimeters, so it is small enough to not work about this. That's why in the end of the in the end, you see here means that your particle size is smaller than the beam size, and then you'll see. Okay. Okay.
Thank you very much. Okay, so let's have the speaker. I think the next speaker is Adriano Alencar, also from the Institute of Physics. Vai usar seu próprio.
Usar o seu próprio computador. Eu te mandei o link. Aqui tem o ID.
Você mandou por. Ah, de Thiago, né? Isso.
Aqui tem o ID, se você quiser.
Ah, você me dá aí.
Você preferir.
Ah,